Good afternoon, class. Today we're going to work our way through Practice Exam 1, and basically this is the same structure you'll see in the final, or in the regular exam. The biggest difference, obviously, there's going to be slightly different questions, but it will follow the same format, so this is a good exercise to kind of walk through. So first, make sure you always write down your name, and your WID, and your section number. And then we get to our questions. What is encapsulation? And the first page is going to be theoretical questions. So this is object orientation in theory. And the second page is specific C# language vocabulary. So keep that in mind. First page, theory. So what is encapsulation? Encapsulation in computer science is the idea of encapsulating state and behavior into classes, objects, modules, all of those kinds of things. Basically, putting related things together and then potentially isolating them through information hiding so that we only allow them to change in well-defined ways. So what I want for these kinds of questions is, in your own words, explaining your understanding of what that is. So if you want to use an analogy and talk about how it's similar to cells, for example, is one of the examples we used in the textbook, or if there's something that makes more sense in your own personal experience, that is fine. But I want a several sentence answer for these. And then after you've answered, make sure that you circle how confident you are on a scale of 1 to 5. We use those confidence ratings. We don't look at them while we're grading. We come back and look at them afterwards, and that kind of gives us an idea if you're overestimating or underestimating your understanding. That also gives you that same knowledge. And then also, if you do mark those at the end of the semester, if you are one of those borderline grades where you are 89.98%. If you've been doing this, that's when I'll give you that bump to the A range. So it is useful to do those. Question 2, describe the relationship between classes and objects. So what is a class? What is an object? A class is the template that describes the structure of an object. So you say what variables it's going to hold, what types they are, basically all the state that it needs to hold, as well as the definition of the functions. When you construct an object from that class, it gets the type of the class and it gets all that storage laid out for it according to that blueprint, and then it has the individual values that you're going to assign to that particular object. So an object is an instance of a class. Describe the purpose of inheritance. So we use inheritance to generalize, if you remember from your UML chapter, that was the word we used for it, to generalize shared state and behavior into a base class, and that can then be inherited by several derived classes, and they don't have to recreate that state or behavior. So it helps eliminate a lot of code duplication, and it makes our software potentially more maintainable for the long run. All right, then we get into C# specific keywords. So there'll be several questions on these. So in this case, what does the keyword protected mean when used with a field? So protected is one of the access modifiers that determines where this particular member, in this case a field, can be accessed. Private means it can only be accessed within that class itself. Public means it can be accessed from anywhere. Protected means it can only be accessed from this class itself and its descendant classes. So anything that inherits from this class also can use that field. And by access, we mean it can read from it and it can write to it. Remember, a field is just a variable that belongs within or is encapsulated within an object. What does the abstract keyword mean when used with a class? So abstract is part of our inheritance hierarchy. It just means that when we use it with classes, that class is intended to only be used as a base class, and it cannot be instantiated on its own. So you can't create an instance of that class. An example from your projects, the side class. It is intended to be a base class for all your sides. It provides some shared functionality, but you can't construct a side. You can only construct one of the specific kinds of sides that inherits from that base class. And what does the new keyword mean when used with a method? Well, in the inheritance hierarchy, you can override methods. New is similar in that it allows you to define a new version of the method, but it does not override the existing version from the base class. So what you're actually doing with the new keyword is creating a brand new definition of that method that will be used when you're treating your object as the derived class. But if you're treating it as the base class, so if you store it in a variable of the type of the base class, it will use the base class's method. So you actually end up with two method definitions, and depending on the situation, you're going to use one or the other. That's why, for example, we don't really usually want to use new. We actually really want to override the method in the base class, but in order to do that, that base class method needs to be defined as virtual, abstract, or already be an overridden method, so we can further override it, because we can't override a method that is not one of those. All right, so here we get into our coding questions. We have, for example, a code listing here. Given the following code, what will be printed to the console? We have cookie. Its kind is a cookie. We have a sugar cookie, which inherits from cookie, who overrides this virtual string kind. So, and that gives us a sugar cookie. We have a public class chocolate chip cookie, then it also inherits from cookie, and it is declaring a new string kind for a chocolate chip cookie. And then we have a frosted cookie, which is extending the sugar cookie class. So it is also by default of that inheritance chain, overriding or inheriting from cookie. And we construct a list of cookies that includes a cookie, a sugar cookie, a chocolate chip cookie, and a frosted cookie. And then we're going through a for each, and notice we're using the dynamic variable keyword here. So this cookie variable is going to be whatever the most derived type of the cookie in this list actually is. And then we're printing out the kind of cookie that we're dealing with. So let's walk through it. Our first cookie, as we iterate through this, is going to be a regular old cookie. So when we grab its kind, the kind we're going to grab is the string a cookie. So the first thing we're going to print out is a cookie. And I'm going to go ahead and write this up as an answer. Question 7. A cookie. And it's printed to the console, so it won't have quotes around it, but it's a string. And the C is actually lowercase, so I should probably do that 100% correctly. The next one is a sugar cookie. So a sugar cookie inherits from frosted cookie. Frosted cookie, back up. Sugar cookie, straight up sugar cookie, inherits from cookie. But notice it overrides the kind, so its kind is going to be a sugar cookie. So when we print that, we would get the string a sugar cookie. Look at that next one, down here we're creating a chocolate chip cookie. That inherits from cookie. This one uses the new keyword, so this will only give us this kind when we're treating it as a chocolate chip cookie. Now we're storing it in a list of cookies, so in that list we're treating it as a cookie. So we would not be using this kind, but we would be using this kind definition. However, we are then assigning it to this cookie variable, which is of type dynamic. Because it is dynamic, it will use the most derived version of the class, which in this case is the chocolate chip cookie, which means we are using this particular string, the one that has a chocolate chip cookie. So we would say a chocolate chip cookie. And then we go down to our last one is a frosted cookie, which inherits from sugar cookie. Notice that it does not override kind, does not define a new version of kind. So we're going to have to look at the sugar cookie for its kind, which is an override. So it's going to give us a sugar cookie. So even though it's a frosted cookie, the string we get back out is a sugar cookie. And that would be our answer to question 7, which is what would be printed to the console, given this code. Question 8. Rewrite the calories field of class chocolate cookie to use a property. So we have a public class chocolate cookie, and then we have a public uint calories 78. So this right here is not a property. this is a field, and we can tell it's a field because there is no get or set accessors defined. That makes it a traditional field. We want to rewrite that as a property. So let's go ahead and I'll add another code block here. Public class, and you guys are going to be doing this on paper, but for ease of presentation, I'm typing it up in Xamarin. So chocolate cookie extends cookie, and then we need to declare a public uint that has calories. Public uint calories equals 78. So this is currently a field. We want to turn this into a property. There's a couple ways we could do this. We could declare a getter, and this is auto property syntax. So now we have a getter, and we're going to initialize it to 78, which means we will always get the value of 78 out. In this case, the property, we didn't define whether or not that should be read-only, so potentially we could also have a setter and just use that default value. This will actually duplicate the exact functionality of the field because we have the ability to both get and set it, and that's public. If we did just the get, then it's a read-only. So that's one way of defining that property. The other way we can do it is, instead of using the auto property syntax, we can use a private backing field. So a private uint calories, and set that equal to 78. And then our get and set would return that and set that. Remember, the setter is a method that receives a value as a parameter, and that value is the whatever was assigned to that variable or to that property, and the getter is a function that needs to return something of the type. So we're just using this private backing field as the storage for this property. If we use an auto property, this basic functionality is provided by the compiler, so it does create the space in memory to hold the value and to retrieve the value. The difference is with the getter and setter, now we can actually go in and tweak what those methods do and add some extra functionality. So either one of those would be an acceptable answer. You have the calories with capital C is now a property. So you can use the auto property, or you can use the fully defined property with a private backing field. And if you look, the provided box, all you have to do is write this part in because we've given you the class definition around it. Okay, complete the method of count cookies of type to count the number of cookies in cookies that are of type T. So we have coming in this method, public static int, is going to return an integer, cookies of type T. This is a templated method, so this T represents a type of cookie that we're interested in, and then we're going to count the number of cookies in this IEnumerable who have that type. So this could be just like the list up here. We could have maybe a sugar cookie, a chocolate chip cookie, a frosted cookie, a bunch of those. We want to know how many of a specific type we have. So let's add another code editing here. And I'll go ahead and add the method definition as well. Static int count cookies of type T, IEnumerable cookies. And of course you don't have to write this part. And it's going to complain that the cookie class is not defined. That's fine because we're just using this workbook to show our code. Let me pull this up a bit so we can make sure we can all see it. So we have an enumerable, and we're trying to count something in the enumerable. There are lots of different approaches we can use to do this, but the one you're probably most familiar with is to use a for each or a for loop. Either one would work fine. So for each, example, cookie in cookies, and we need to store this in a variable, or we could use a dynamic. Either one of those would work. I'm just going to use a var right now. And we want to count something, so we need a variable to count that as well. So we'll do an int count equals 0, start it at 0. And then inside this for each loop, we want to look at the individual cookies and determine if they're of whatever type t is representing. So t we can use as a variable within this class or function definition to represent a specific type, like a sugar cookie. So in that case, we would want to count if that cookie is of that type. So how can we determine if cookie is a specific type? And if you remember our chapter on casting, we could use the is operator, which checks, is this something we can cast to be this thing? And we can just check if the cookie is t. So if that type was sugar cookie, this would check, is this cookie a sugar cookie? And if that's the case, we can increment that count by 1, and then at the end of this for each, we want to return that count. And that gives us our enumeration. So that's the answer right there. We just need something like this. We could also do a for loop and iterate over the list using an index variable. That's also acceptable. There are some other ways we can do this with link, which we're going to cover later in the semester. So there are a lot of possible techniques. And if you're wondering what would it look like to actually use this method, we would say whatever class this is defined in, cookies, maybe dot count cookies of type. Well, I'll just do it this way. We would want to provide the type, so we could, for example, say sugar cookie, and then we provide our list of cookies, which this is actually using the list we defined up. We don't have a defined list, so we'll just say list of cookies. So if we had a list of cookies that contained 3 sugar cookies, 5 frosted cookies, and 10 chocolate chip cookies, it would use this as your value t, and it would count every one that could be cast to be a sugar cookie. And we said we had some sugar cookies, so it would definitely count those sugar cookies. And then we said we had some frosted cookies, which from that earlier definition inherits from sugar cookie, so it would also count the frosted cookies, but it would not count the chocolate chip cookies. So that's kind of the use of a templated method, which you guys used last semester. I know it's probably been a while since you've seen that, so it's good to maybe just dig in and review that a little bit. And especially what I want you to take away is we really want to be able to use the is keyword, which checks if something can be cast. There's also the as keyword, which will cast it to that thing, or null if it can't be cast to that thing. All right. Now we have some more code questions, and notice that these deal with the code on the final page of the exam. So if we scroll down to the final page of the exam, we have a code listing, and you will often have a code listing or a UML diagram or some combination thereof, or maybe even a data table on the last page of the exam. And a few semesters ago, I had the suggestion of moving all that to the last page of the exam, so when you're in a class, you can rip off that last page and just set it to the side and use it for all the questions it needs to be used for. And that was a great suggestion, so I have since moved it all to the last page. And you notice there are a bunch of questions here. They all reference that last page. Okay, so the first one, draw a UML diagram for the provided smart room class. So this is our smart room class here. And we want to draw a UML diagram for this. So I'm going to fire up Paint, bring a little Paint window over, and we're going to draw ourselves a little UML diagram. So the first thing we see in that is we have the class name Smart Room. So we want to have some text, Smart Room. So the class name goes in the very first box of our UML. And when we're doing that UML, we want to, tools, pencil, we're going to have basically a box. My advice is draw the left side and the top line, and then put in all your stuff before you fill out the next few lines, so this side and this side. Because if you draw this vertical line, it always happens that something is longer than that and overflows your box and doesn't look very professional. So let's go ahead and just do it this way. So we have our smart room. The class name goes in the very top. If it is a static class, then it needs to be italicized. If it's an enum or a interface, then it needs to be use those stereotypes. In this case, it is not abstract, it's not static, so there's no special formatting, just the name. Then we're going to have the next box is all of the fields and properties. So we have a private thermostat. Private is indicated with a minus sign, and it is variable name is thermostat, lowercase t, and the type is thermostat with a capital T. So that's one row. The next one we have a square footage, which is also private, so negative. Square footage is the name, colon, and then the type, which is double. And notice that we have a default value of 0. We indicate that with an equals 0. Then we have public double square footage with a capital S. This is a public property. Notice it has getters and setters. So in that case, it's public, so we use a plus sign to indicate. And we're going to do a square footage with a capital S. And its type is double. And then because this is a property and it has both a get and a set, we're going to use a stereotype to indicate that we're using get and set. Stereotypes are used to denote language-specific features. So UML is meant to be language agnostic. It really shouldn't matter what language we're using, but the reality is oftentimes we do need to specify things that are specific to a language, and we do those with stereotypes. So that indicates that this is going to be a property. And because we know that the actual value it's returning is this private backing field of square footage, this 0 means that this is technically going to default to 0. So we could add that as a default value as well. And then we have current temperature. This is a get only double. So again, it's a property. So we'll do current temperature. And its type is double. And then because it's get only, we only specify the get in the stereotype. And then we have target temperature, also public, also a double, and it has a get and a set, so we'll do both. And then we have a constructor, which is a method, and that wraps up our class after that. So we will go ahead and close off this part of the box, which is where all the properties and fields go, and we'll write our methods. So we have a constructor, so it is going to be smart room, and then in the parentheses we specify each of the parameters. So we have a square footage whose type is double, comma, and then we do the next parameter, which looks like it's the thermostat of type thermostat. And that is it for arguments. And then if this wasn't a constructor, we'd have to do a colon and the return type. But because it's a constructor, we don't specify a return type because they don't really have a return type. They construct the object, and that's the object's actually what they return. But we don't normally think of it that way. And that is the only method that we have defined for this smart room. So we are pretty much done. We can go ahead and close off our boxes. And there we've done our UML diagram for the smart room class. That was question 10. Question 11, write a new read-only accessor, delta T, which provides the difference between the current and target temperature of the room. So read-only accessor, that means we're looking for a property that has a get method but no set, and it's going to give us the difference between current and target. Difference means we're going to subtract those two. So let's go ahead and just add our accessor. We want this to be public, and we called that delta T. And it's going to provide the difference between, and that's going to be of type double. So it's a get only, that's what the accessor means. And we're going to get the difference, so return the difference between the target temperature and the actual temperature. And then we want to make sure that we put those current and target. So it's actually current temperature, not actual temperature. And said difference between current and target. So this actually needs to go on the other side of the subtraction. You want to make sure you do that in the right order based on what you're asked to do. So the difference is the current temperature and where we're targeting. So if our room is hotter than we want it to be, the delta T is going to be positive, and if it's negative, that means we're colder than we want to be. Okay. Now this is not the only way we can write this. Get accessors we can also write with lambda syntax. And if it's a get only, we can also even more abbreviate that by just doing lambda syntax directly off the definition. Those are all three viable ways of defining a getter, especially a read-only getter. Okay. Next question. Create a derived class from SmartRoom named LitSmartRoom that includes 4 Boolean properties, lights A, B, C, and D, with getters and setters, plus methods switch all lights on and all lights off that set all 4 to true and false respectively. So we're asked to write a new class called LitSmartRoom. So let's go ahead and create another box to start working in. And I'm going to rearrange these a bit so that it's easier to see what I'm doing. And go ahead and chew up some of that space. There we go. Okay, so we are going to create a new class, public class, LitSmartRoom. And it's derived from SmartRoom. So we're going to use the colon and SmartRoom. And this means that we get to use everything in SmartRoom is just automatically there for LitSmartRoom. So it has all the thermostat stuff that we already seen. We're defining 4 Boolean properties for lights A, B, C, and D that have getters and setters. So public bool light A has getters and setters. In this case, there's no reason we can't use the auto property syntax, so I'm going to use that. We could also define these with private backing fields, which is perfectly fine. If you want to do that, we will accept it either way. But it's a little easier to write the auto property syntax if that's all we need. And a lot less writing. And if you're like me and using a pencil is something that just not as easy as it was when I was younger and I did a lot more, it does start hurting my hand after a while. You may want to use the short form. Okay, that gives us our 4 Booleans. There are no default values specified, so we could just leave it like this. In this case, these will all default to off or false, because anytime you declare a Boolean and you don't give it a default value, it will default to false. And that makes sense here, that we would start with the room, not have the lights turned on, a little more energy efficient that way. Then we have 2 methods we need to write, switch all lights on and switch all lights off. So public void switch all lights on. I'm going to go ahead and move this down a line so it's a little easier to read. And this method should switch on all of those lights. So light A equal true, light B equal true, light C equal true, light D equal true. Pretty easy. And we do the same thing for switch all lights off. Light A equal false, light B equal false, light C equal false, light D equal false. Okay, that is our class in a nutshell. A couple things, you notice we didn't use XML comments on these. I don't require the XML comments in a testing setting just because it's more work, and we're working with a limited amount of space, and while it's important to do For the purposes of an exam, it's not really what we're looking for, so it's fine if you don't put comments on those. However, if you're doing anything and you're like, I'm not sure if these should be on or off, I really want to acknowledge that I was aware that was something to think about, you can put an annotation. So just write a note on the side saying, I'm assuming you want all the lights to be off. And I will say, yeah, that was a good assumption, that works. Or I'm assuming you want them all on, so I set them all to true. That is also fine. That just helps convey to me that you understand what you're being asked to do and kind of where you're taking that idea moving forward. Okay, let's go back to our exam. I think that was our last question. Oh, no, we have tests. Let's not forget these. Okay, so complete the following test of the Smart Room class. And we have a mock thermostat, which we're using for our thermostat here. And notice that it has two properties, two fields for current temperature and target temperature, which are just 75 and 75. So this is fulfilling the role of the thermostat. And then we have theory should be able to set square footage to a valid value. If you remember, actually, if we go back and look at our square footage, we have the value must be positive, must be greater than or equal to, or greater than 0. So it has to be positive and not 0. That is a constraint that actually belongs in our UML diagram. So if we come back into our UML diagram, we'd want to make sure that we added that. The square footage has a constraint. Constraints are done with a curly brace, and we'd say square footage greater than 0, like that. That's how we do a constraint. So that shows that we understand this value is always going to have to be greater than 0. So I'm sorry I missed that earlier. That's something we should have in there. So with that idea, square footage to a valid value, we have inline data of 3,000, 24.023. These are all valid values because they're greater than or equal to 0. So we want to test to make sure that that is a possibility. And we can go ahead and create another box to be our test. And we would use an assert to do the test. And we need an instance of Smart Room to work with. So we are going to go ahead and create one, var smart room equal new smart room. And if we go look at our constructor for smart room, because remember we had a constructor, it takes the square footage and it takes a thermostat. So we also need a thermostat. We're going to use that mock thermostat, which was defined at the top of the test file. So if we go back up to the top of our test, we have this mock thermostat. It provides a current temperature and a target temperature. It has a parameterless constructor, so we're going to construct that. And then our smart room, we are going to provide, when we construct that, we need to provide the square footage as the first argument and the thermostat as the second. And the square footage we're getting from our test method as the parameter square feet. So we would pass in square feet, comma, thermostat. That constructs our smart room. It has that particular size of square footage applied, hopefully, and we want to make sure that we were actually able to set it. So we want to check that the constructed smart room has this square footage we asked for. So we're going to do an assert.equal, and we're going to check our expected value, which is square feet. Again, what came in from our argument. And we're going to check that that is equal to smart room.square, and I believe it was footage. Let's double check our method name. Square footage. So the property is square footage. That's going to check that the square footage of the smart room equals the square feet, which we set it to in the constructor. So ideally, you set it to that, it was a valid value, we should get a valid value back out, the exact same value, in fact. So that's that first test. Second test, should not be able to construct an invalid room. So for this, again, we're taking in footage, which is the amount of space in the room, and we're doing an assert.throws. This makes sure that a particular kind of exception is thrown, in this case an invalid argument exception, when the body of this lambda expression is run. So in this lambda expression, we create a room using that footage that we supplied and a new mock thermostat. So mock thermostat should work. We have that class defined for us right here. This footage needs to be an invalid value. So what possible invalid values could we pass into this method to cause some problems? And we're going to do that obviously with an inline data. So let's get that up so we can see the theory. We're going to do an inline data, and the inline data takes a list of parameters which are going to be passed in here, so arguments for that double footage. So remember, we said the constraint was square footage needs to be positive and greater than 0. So we could pass in 0, that should be an error, and we could pass in a negative number. And that could be an integer, or we could also pass in maybe a negative 0.3344, so a floating point number. All of those should cause that exception to be thrown, so that's what we'd want to supply as our inline data to that theory. A fact should pass through thermostat temperature, so that means basically that if we ask the smart room what temperature it is, it should tell us what the thermostat is telling us. And the thermostat says the current temperature is 75 degrees. So in that case, let's do one more of these. We need to write our method, which should pass through thermostat temperature. We can just create a var smart room, new smart room. We need to give a room measurement and square footage that'll be legal, so we'll just use 100, and a new mock thermostat. And we know the thermostat has that value. In fact, let's create our thermostat up here. Var thermostat, new mock thermostat. And then we can just pass that one in specifically. And now we can do our assert dot equal, and we expect the thermostat dot current temperature to be passed through or be the same as the smart room dot current temperature. And that's what we're looking for there, that we do the comparison between the thermostat and the actual. And then should be able to set target temperature. We want to be able to take a smart room class and new smart room, do 100, a new mock thermostat. Actually, let's do it the same way here. Okay, and once we have that thermostat in the smart room, we want to be able to change from the smart room and set current or target temperature to be, let's say we want 70 degrees, which is not the, sorry, not there. Not what the thermostat is set to. Nope, target is 70. Never mind. We don't want to set it to what the target actually is. Let's set it to 73. So we've set the smart room's target temperature. We want to make sure that when we do that, the thermostat's temperature also gets set to that value. So assert dot equal thermostat, or sorry, actually we can just use the 37 since this is our test, or not 37, 73. And we can say, is the thermostat's target temperature equal to that 73? So we set the smart room's target temperature. Smart room should set the thermostat's target temperature to match what we just set, which was 73. So if this assertion works, we know that it's correctly done its work. And that is last question on the testing, and then we get back to our code listing. That is our full test. So that should give you a pretty good idea of what we're looking at in terms of exam 1. Kind of the format will be very, very similar to this. We will have a 1 page of vocabulary questions that are on the theoretical side of object orientation, 1 page of vocabulary questions that are on the C# vocabulary, these need to be a short answer, as in several sentences of answer, and explain them in your own words. That's very important. That's what I'm looking for. I don't want to see quotes. I don't want you to just memorize definitions out of the textbook. I want you to explain how you understand them. And then we have some coding questions that are just kind of short answer ones, and then we're going to actually do either some code writing or some UML on paper. One final note, as we talked about at the beginning of the semester, when we grade these and get them back to you, you will have a week to correct anything that you got marked off on. And if you turn in those corrections and actually correct them, you can earn back all the points that you lost. So really, this exam is not meant to be a benchmarking exam. This is really to help us understand where you are in your learning and help us identify if there's anything that we really need to address moving forward in your understanding. So good luck, and I will see you next week for the test.